Hi, my name is Javier Alvarez, and I'm a Principal Research Manager at Microsoft Research in Cambridge, UK. I have been in Microsoft for the last 8 years, and for the last 5, I have been specializing in healthcare and computer vision. I lead medical imaging AI as part of the InnerEye team, and in the InnerEye team, our mission is to democratize medical imaging AI to empower researchers and healthcare organizations to build AI solutions in Microsoft Azure. We want to advance the state of the art in medical imaging and transform it into a more quantitative science. Medical imaging is used across almost all the medical domains, and it's the biggest source of data in healthcare. Medical images allow us to look inside patients for diagnosis, but they are also extremely useful when tracking an existing illness or for treatment. Each year, 500,000 patients are diagnosed with cancer and receive radiotherapy treatment. In radiotherapy, we use high doses of radiation to kill cancer cells, and at the same time, we try to minimize the damage on the healthy tissue and organs. Radiotherapy planning is very time-consuming. In radiotherapy, we use a linear accelerator or LINAC that delivers high doses of radiation on the target moving around the patient. In order to program the LINAC, we need to acquire a 3D CT planning scan, where clinicians must delineate or segment manually with high precision the tumor and the healthy organs in 3D. This can take between 30 minutes and 2 hours depending on the case. As part of our research collaboration with more than 20 hospitals around the world, we ask ourselves, can we empower clinicians with clinically acceptable AI models that can accelerate radiotherapy planning? This question has been addressed in a recently published JAMA Network Open article titled Evaluation of Deep Learning to Augment Image-Guided Radiotherapy for Head and Neck and Prostate Cancers. One of the barriers for clinical adoption of machine learning is generalization. When we think about generalization for segmentation models, the first challenge is that we need to make sure the models work on unseen data, but also to be able to scale the models to work for different cancer types and body parts. To try to overcome this, we have worked with hospitals around the world in Australia, Europe, New Zealand, North America, and South America. We divided their data into main sites and external sites for evaluation. We then tried to train machine learning models for prostate cancer with 519 images and 242 images for head and neck. The segmentation model architecture that we used is a state-of-the-art unit 3D with 39 million trainable parameters. We enhanced the model in many ways, including image sampling functions that are learned using strided convolutions instead of max pooling. Upsample tensors pass through nonlinear activations before concatenations to increase the representation power of the model. We also added residual connections on each consecutive convolution, and finally, dilated convolutions in the encoders to capture large contextual information. We also had to do many distributed training optimizations in order to train our ensemble models. We use Azure Machine Learning Services to parallelize training on V100 GPUs using 5 virtual machines. We also implemented model parallelization and mixed precision representations to be able to fit really big patches during training and to be able to run inference on the full volume. In order to decide the clinical applicability and performance of the models, we compared the output of the model with 3 experts, contouring 10 images for each radiotherapy domain. We found that the model performs within the human expert's variability using a statistical testing. Also, we tested on external datasets from 3 clinical sites. These sites had different imaging protocols, CT scanners, and patient preparation. We also found that the model performs consistently on main sites and external sites, making us confident on the generalizability of the model. Finally, we measure the clinical value of our models in terms of time reduction. For head and neck, we found that we can reduce the time from 73 minutes to 5 minutes. This is more than 90% time savings. If you want to try the results from our research, all our code is now open source. You can go now and download it on github.com. Our open source toolkit allows you to reproduce our state-of-the-art models for radiotherapy segmentation. We also have models for classification of 2D and 3D images, as well as models that take a sequence of images to generate a prediction. Our toolkit is built on top of Azure Machine Learning Services and allows you to leverage scalable GPU clusters, as well as follow the best practices to build robust AI models with MLOps. Our toolkit is built on top of PyTorch, but provides configuration templates for different clinical scenarios that can help you build useful models with minimal code. It can be as simple as uploading your dataset to Azure Storage, reusing one of our configurations, and running your training on Azure Machine Learning. If you want to work as a team at the scale, our toolkit builds on top of Azure Machine Learning Services to make sure your models are reproducible, traceable, deployable, and we also offer model comparison, using statistical testing to check that when you change your data or your code, your models are always getting better. The models trained with our open source toolkit can be deployed and integrated with clinical DICOM workflows seamlessly. Usually, we configure the scanners or the clinical database to forward images to the InnerEye gateway, and the gateway can filter and select the correct model depending on the image metadata. It can also perform anonymization and send images to Azure for inference on GPUs. Once the segmentation is ready, the gateway will send the contours back to the database, and clinicians will be able to review the output of the model and use it for radiotherapy planning. Depending on your information governance requirements, you can also deploy the same solution on premises using Azure Stack Hub. To learn more about the InnerEye project, feel free to visit the InnerEye website. You can also take a look at the InnerEye GitHub repo, where you can download our code. If you want to check the latest news about the project, please go to the research blog. And finally, you can also read our recent clinical paper published in JAMA Network Open. We look forward to researchers and healthcare organizations to build on top of our toolkit to ultimately benefit patients around the world. Thank you.